So what's required in your project? What's required in your project is to do the following, okay? Should be able to have the spectrum of your signal. So whatever, for example, you found that it looks like this, okay? And maybe you found that like here, where you start ignoring the rest is something like 5K or 6K kilohertz, okay? That's as a function of frequency. And this is your X of omega, or that's your spectrum of voice that you have. Your project is a 3-band equalizer. What does this mean? It means that it should be able to take that frequency domain signal and then divide that into 3 pieces. Okay? That spectrum that you see there should be able to divide it into 3 pieces. And then each piece of those, you should be able to control its magnitude, increase the magnitude or decrease the magnitude, which is what we call amplify the band or attenuate the band, which is what you see in your equalizer as going to the plus side or the negative side, okay? If you have an equalizer, for example, mostly they are 5 or 7 band. The 3-band is a very simplified equalizer, okay? You have many switches, or electronically you can switch between band 1, band 2, band 3, band 4, and so on. And for each one of them, you can increase the magnitude above 0, or
for each one of 3 pieces.
Yes, increase or decrease. So you need to attenuate or amplify the magnitude. Only the magnitude. You don't touch the phase, okay? And I will reflect on that in a minute, okay? So how do you do that? First of all, you have to take that signal and divide it into those 3 pieces, right? So that you can control each piece independently. And then at the end, you have to combine them back to retrieve the original signal after being affected with that amplitude change, okay? So you have your voice, which is a time domain signal, right? So that's X of t. What the first thing that you do, now that's on the software. The first thing that you do is you need to take the Fourier transform of that signal. Okay, that's what you do when you do the FFT command, okay, on MATLAB. Now what's produced on the other side is X of omega, and as we see, this is how X of omega looks like. Something like this, okay? And let's say you stop at this point. So this is what you care about, this part. This is your full voice band. As we said, for example, let's say 6, because 6 is easier to divide into 3 pieces, okay? 6 kilohertz, for example, eh? Frequency domain, because we took the FFT, right? So we are looking at the signal in frequency domain, right? And then now you need to divide that into those 3 pieces that I talked about. So this is one piece, this is the other piece, and that's the 3rd piece. So the other piece is green, this piece is blue, and the last one maybe red, okay? These are the 3 pieces. How do you do that? How do you take those 3 pieces? You need to take this signal, which is the combined signal that you got out of the FFT, and you do 3 effects on it. So the same signal will go through 3 paths. This means that you will produce a new variable in MATLAB, because you are dealing with MATLAB now, you don't really go through a particular flow. So you will take that signal, do something on it, and produce one variable. That's the first path. Do something on it, produce a second variable, that's the second path. Do something on that spectrum, produce a third variable, which is your third path, okay? So what should I do? If I want to get only the first part of the signal, what do I need to do? Multiply it by a square function, right? Which is only at this part. If I say that this is, I call this omega 1, I call this omega 2, and I call the last one the bandwidth of the signal B, okay? So these are frequency ranges, right? So the first part of the, so I take the signal, and the first thing that I will do with that signal is multiply my signal X of omega with this guy, right? A square with height 1 and with width omega 1. What's going to be the outcome of this multiplication? If I take that square function, multiply it by this whole signal, what do I get? I get the first part that we see here, right? Okay, so what you will get out of that is going to be this blue guy, So the output from that is going to be this guy. Okay? That's what you will get, the first part of the signal. Now, for the second, same idea. Okay? I have to multiply it by a band pass filter. So that first one was low pass filter. Band pass filter that takes the range from W1 to W2. So again, my X of omega is multiplied by some filter here, which looks like this. Again, amplitude is equal to 1, and the width is from omega 1 to omega 2. Okay? From frequency F1 to frequency F2. Okay? And then the result of that multiplication is going to be the second part of your signal, right? Which looks like this. Okay? The green part from the signal. Okay? And then the same I will do for the last part. So X of omega multiplied by a high pass filter, which is again from omega 2 up to B, and it's with magnitude 1. And when you do this multiplication, what you will get is going to be the last part of your signal, which is this part. Okay. Now you got the three pieces of the signal, right? Now you didn't do anything. You just cut the signal into three pieces and you put them into three variables. The first variable, if you take it and multiply it by a value greater than 1 or a value smaller than 1, then this is going to do what? Amplify or attenuate. Okay, so that's the amplification or attenuation. So simply each one of those, you're going to take it through its own path. It's a bad color. So you take this through its own path here, and you put it through a multiplier, gain, or attenuate. Okay, that's simply a multiplier. You multiply it by a value. That value can be something that the user enters from the screen. Or if you want to do something very fancy, but it's not required here, you can use MATLAB user interface, but that's complicated to use if you are not used to it. Just simply a value that can be taken from the user at the start of the program to say what's the gain of the first band, what's the gain of the second band, and so on. Now,
Times gain, gain over
gain or attenuation. Gain if it's greater than 1, attenuation if it's smaller than 1. Okay? Similarly, you will do the same for the second one with another gain. So that's going to be multiplied by gain or attenuation. And the same for the last one is going to be taken through gain or attenuation. Okay. Now you got your signal, the three bands, each one of them amplified or attenuated. What's the next step? Combine them and produce them again at time domain. You need to produce them in time domain. So that's gonna be simply, you will take those three variables as frequency domain variable, right? This guy, and this guy. And you need to combine them together by a plus. What you will get from this plus, okay, is going to be again the same spectrum but affected by whatever amplitude. So it might look like this, okay? Okay, whatever. You increase the gain in some parts. Let's say you pick the middle one, you increase its gain. You pick the first one, you decreased its gain. And the last one, maybe you didn't do anything to it, so it stays as it is. When you combine them, it's going to be, in terms of magnitude, it's going to be a differently shaped spectrum. All of this is on the magnitude of the spectrum. Okay? So we started here. This figure is the magnitude, not the phase. You don't touch the phase. Okay? And then at the end, you take the magnitudes, you combine them, and you multiply them with the phase as it is. You don't touch the phase. Okay? Now what will happen in this case is you will get a signal which is, for example, if it was music and you decided to reduce the magnitude of the lowest frequency, then you will see that the drum, for example, in the music becomes lower and you can hear now the other image from its more, or vice versa. but it is still audible voice and it is still music recognizable. It's not just scrambled. Why? Because you didn't touch the phase. Remember we said most of the information of the time domain signal, how it varies with respect to each other, how it affects your ear, how it affects your eye if you are looking at a picture, is stored in the phase, not in the magnitude. Of course, given that, you don't take the magnitude and you change them significantly with respect to each other. So if you decide, for example, to cancel parts of them, multiply them by zeros, and another one you multiply it by 1 million, of course you're gonna scramble the signal in this case, right? But if you just do relatively close variations of the magnitude with respect to each other, and you don't touch the phase, you will get still a very nicely audible signal with those effects that the equalizer does. Reduce the sound of the drum, increase the sound of the violin and the high-pitched pianos and so on. All of this can be done by playing with those different bands, okay? Now this is the software part. What would you do in the hardware part? In the last thing is, just to remember, you need to retrieve this signal back in time domain. So you have to bring it back as x of t. So you have to do an inverse FFT before taking your combined signal into the speaker of the computer. After combining them, they are still frequency domain signals. If you try to put that to the speaker, you will get some nonsense. You have to bring it back to time so that the speaker gives you an understandable audible voice, okay? Now, in terms of the circuit, when you implement the circuit, you don't need to do most of these things because in the circuit, this part, which is the filtering, is already performed by those RC filters that you will put, right? The only thing is, you know that these in frequency domain would have this representation, but the signal going through the circuit doesn't need to know that. It's a time domain signal and it flows nicely, right? We do this in the software because in the software we are trying to understand what are we doing by our hands, right? The circuit is already physically doing this effect without really converting the signal from one thing to the other. It's just the audio comes from the microphone, it goes into the RC circuits, which are designed to be a certain RC circuit to be the lower band one, and then another one designed to approximate the band pass, and then another one designed to approximate the high pass, okay? And then the outcomes from those are gonna go through some amplifier circuit with a controllable gain through a potentiometer or whatever, right? And then after that, you need to combine those three voltage signals. They are voltage signals. So you just need to add them one after the other, cascade the voltages, take the highest and the lowest, whatever. You'll see how to do it in the circuit itself, right? And then that final added voice, you just take it to the speaker. You don't need to convert to frequency and then back to time. This is all happening in our minds here and the software to understand what we are doing. But the actual physical circuit is already dealing with the signal in time domain and doing these effects, right? The problem is if we try to do it here in software in time domain, what does this filter, for example, what does it mean to filter part of the signal, which is just a time domain signal? How can I take part of the frequency out when I'm doing this with software? I have to take it to frequency to see what exactly I'm doing with the frequency domain, right? But the actual circuit is doing this, yes?
What should our ideal bandwidth be? Because right now, I feel
There's no ideal bandwidth.
So
I mean, there is a range that's acceptable.
What is that?
I'm not going to tell you. You try it in the experiment. Okay? If you do a proper experiment, you should be within that range. Okay?
As in, like for ours, because it depends on who, like the different audios.
I told you to try to mix certain types of audio, right? If you do that, you might get different ranges still, but it's not going to be outside the acceptable range. Okay? Any other questions?